Okay, so for the last topic for this section, we're going to talk about compressibility of the fluid in Bernoulli's equation. In a lot of these problems, we have been assuming an incompressible fluid. And so let's try to look at what happens when the fluid is compressible, okay? Now this is a special case, and we're going to dig into this more when we get a little bit further on, but this is just to give you an idea of why we keep saying we're dealing with incompressible flows. Okay, so the example is we've got a Boeing 777, flies at Mach 0.82. I'll explain that more in a second here. At an altitude of 10,000 kilometers in a standard atmosphere. Okay. Determine the stagnation pressure on the leading edge of the wing if the flow is incompressible and if it's compressible isentropic. So I'm just going to abbreviate this and say determine the stagnation pressure. All right, so A is when we're dealing with the incompressible flow. So basically what this means, if it's incompressible, is that the density is not going to change as a result of the pressure or whatever else in the system, okay? So the equation to find the stagnation pressure is going to be P2 minus P1. So that's basically the difference in the pressure based on the flow over P1. That's equal to K times MA squared over 2. So I'm going to step through this. So P2 minus P1 is the stagnation pressure. If you want to look at it with the P1 underneath, you could argue that that's like a normalized stagnation pressure or something like that. Okay. K is the specific heat ratio. And you've probably seen this in chemistry or heat mass transfer or something like that. And it's the specific heat of at constant pressure versus at constant volume, okay? And this is gas dependent. You can make approximate estimates based on whether the gas is monatomic or an inert gas versus diatomic, but it does, your best bet is to actually look it up and figure out if it's what the actual value is, okay? MA is the Mach number. So the Mach number is the ratio of the fluid velocity to the speed of sound in that fluid. And this is the first of the dimensionless numbers that we are going to be using to characterize fluids. Okay. What it's equal to, so the equation you can use is that the velocity is over the speed of sound, and the speed of sound is determined by calculating K times RT. So of course this is, in a gas. We have a different method for solving this for a liquid. Okay, so in this case, in this problem, we're actually given the Mach number. So we don't have to worry about calculating it out for the purposes of this, okay? I looked up the quantities, and for air, we have that, I should say air at 10 kilometers in standard atmospheric conditions. We've got the pressure is equal to 26.5 kPa. That's the absolute pressure. The temperature is equal to minus 49.9 degrees Celsius. The density is going to be 0.414 kilograms per meter cubed, and K, which again is the specific heat ratio, is 1.4 for air. Okay. All right, so in order to do this, we're going to use the equation we had above, P2 minus P1. I'm going to go ahead and multiply both sides by P1 so we get an actual numerical value. So we're going to have P1 times K MA squared over 2. So that's going to be 26.5 kPa times 1.4 times 0.82 squared. That's going to all be over 2. So that gives us a stagnation pressure of 12.5 kilopascals. Okay, so that's when it's incompressible. When it's compressible, it's, in fact, specifically when it's isentropic compressible. What is isentropic? Well, this is a special case of a process. Okay, so isentropic basically means constant entropy, and the implications of that is that basically it's a reverse adiabatic process with no heat transfer. So hopefully this looks familiar to you from either chemistry or heat and mass transfer, or potentially thermodynamics. Okay, for that one, we're going to use this equation. And it's a little bit more messy. Hopefully that all makes sense. So we have 1 plus K minus 1 over 2 times the Mach number squared. And all of that taken to the K over K minus 1 power, and then we subtract off 1. Okay. So again, I'm going to multiply by P1 so that we can get an absolute value rather than a ratio, because that way we can compare apples to apples. So we're going to have this 26.5. This is the P1 value, kPa. Okay. Then we're going to have 1 plus K minus 1. Well, K is 1.4 minus 1. That's going to be 0.4 over 2 times 0.82 squared. And all of this, all of that will be to the K over K minus 1. So that's going to be 1.4 over 0.4 minus 1. So when we calculate that out, we end up with 14.7 kilopascals. Okay, so at a Mach number of 0.82, our pressure, which has implications for the lift and drag on the aircraft, is 1.18 times greater for the compressible flow. So what this means is that our compressible flow would have probably both more lift and more drag. When we're at lower Mach numbers, we're not going quite as fast. We're not going to get this drastic a change in pressure, and so it may not matter as much. The pressure may not be that different whether the flow is compressible or incompressible. And in those scenarios, if you're probably less than 5% difference between the two, then it's fine to use the incompressible assumption. But when you do get up to higher values, particularly for gases, you need to be careful because you may not be able to make that assumption.